Suppose we have a point on a surface, in this case being a hyperbolic paraboloid. So the point P has coordinates xp, yp, and the z coordinate is a function of the x and y coordinates. So this point P is in the domain of the function, being a function of x and y. Now suppose we cut this surface with a plane at y is equal to the y coordinate of this point. So in this case the plane will cut a curve out of this surface, where the surface is defined by z is equal to a function of x and y, and the curve that's cut from the surface has the equation z being a function of x, and the y coordinate of the curve is fixed. So this is the curve that's cut out of the surface, in this case being a parabola. So essentially, the curve is the graph of this function in the plane at y equals yp. So this plane is parallel to the xz plane. So therefore the horizontal coordinate of this curve is x, and the vertical coordinate is z. So z is a function of x. Because we're holding the y value constant at yp, so therefore y is not a variable in this function. So if we take the derivative of this function with respect to x, being the function that defines this curve, which is f of x with y being constant, and we evaluate this at this point, which has an x coordinate of xp, then this ordinary derivative of the function of this curve with respect to x at the x value xp, which is the same as evaluating the derivative of the function at the point with coordinates xp and yp on this parabola, is really the partial derivative. So we're differentiating with respect to x while holding y constant. So we define a partial derivative of the function with respect to x using the following symbols to separate it from the ordinary derivative, evaluated at the point with coordinates xp and yp as the limit as h approaches 0. So using a similar notation to define a partial derivative as in a limit definition of the ordinary derivative. So we're taking a limit of f at xp plus h while keeping yp constant minus the function at xp and yp over h. And this is provided the limit exists. So essentially, the slope of the curve defined by this function at point P, which is in the plane y equals yp, is the value of this partial derivative with respect to x, evaluated at this point. And we see here the tangent line to this curve at P is the line that's in this plane that passes through P with a slope given by this partial derivative. So essentially the partial derivative evaluated at this point gives the rate of change of the function with respect to x when we fix the y coordinate at this value yp. So a common notation used for the partial derivative of the function f with respect to x is f with a subscript x, or the partial derivative of f with respect to x evaluated at a specific point, we will put the coordinates of the point in brackets, or you might have the partial derivative of z with respect to x and so on. Now in a similar way, if we cut the surface with a cutting plane, defined by x is equal to xp, where the plane passes through this point, and our cutting curve is this parabola over here, which lies in this plane that's parallel to the yz plane. So in this case, this curve will be defined by z as a function of y. So x is fixed at some value, and y is the independent variable. So therefore the partial derivative of f with respect to y, evaluated at a point with coordinates xp and yp, is the limit as h approaches 0, and we take the limit of the function with x being constant and y being the variable. So we have yp plus h minus the function evaluated at xp yp on h. So note again that x is fixed, in this case to xp being the cutting plane. So essentially that's the same thing as taking the ordinary derivative with respect to y of our function, with x being fixed and y being the variable, evaluated at y is equal to yp. And similarly the slope of this curve at point P, where the curve lies in the plane x equals xp, being this parabola in this case, is the value of this partial derivative of the function with respect to y at the point with coordinates xp and yp in the plane. And we can see that the tangent line through the point also lines in the plane of this curve that has a slope given by this partial derivative evaluated at point P. And again this partial derivative gives the rate of change of this function with respect to y for a fixed x value. And again you'll have similar notations to the partial derivative with respect to x. So you'll have f subscript y, the partial derivative of z with respect to y, and so on. So we can see in this case we have two tangent lines at point P for this surface defined by this multivariable function. Z is f of x and y. As we've seen, there are two ways of differentiating a function of two variables, with the partial derivative of f with respect to x being evaluated at a point where x is the variable and y is held constant, and differentiating the function with respect to y where y is the variable and x is held constant or fixed. So for example, evaluating these derivatives for a hyperbolic paraboloid defined by z is equal to y squared minus 4x squared, taking the partial derivative of z with respect to x means the first term drops out because y is held constant, and the second term gives minus 8x, using the power rule for differentiation. And taking the partial of z with respect to y, we get 2y using the power rule, and the second term drops out because we hold x constant. So therefore, moving in the x direction along this parabolic path, when x is negative, the slope of the tangent to the curve is positive, and when x is positive, we see the slope of the tangent to the curve is negative. And similarly, moving along the y direction, So for example, along one of these parabolas, we see that when y is negative, the slope of the tangent to the curve is negative, and when y is positive, the slope of the tangent to the curve is positive. Now if these partial derivatives are evaluated at point P, having an x coordinate of 1/2 and a y coordinate of 1, then the partial of z with respect to x at this point gives 8/1/2 or -4. And evaluating the partial of z with respect to y at the same point gives 2/1, which is 2. So in the x direction, the slope of the tangent to the curve is negative, as we can see, and in the y direction, the slope of the tangent to the curve is positive. Now suppose we want to evaluate the partial derivatives for the function x cosine xy. So taking the partial derivative with respect to x, we hold y constant, and using the product rule, we differentiate the first term, so we get cosine xy, and then differentiate the second term. So we're holding y constant, so we have minus x by y by sine xy. And evaluating the partial derivative of z with respect to y, we hold x constant, and y is the variable, so we get x multiplied by x by minus sine xy. The definition of the partial derivative can be extended to functions of more than 2 variables. So suppose we have a function of 3 variables, for example, then taking a partial derivative of f with respect to x is equal to the limit as h approaches 0, and this time the difference quotient is f of x plus h, and y and z are fixed, minus the function of x, y, z over h. And similarly, the partial derivative of f with respect to y is the limit as h approaches 0, and a difference quotient involves taking x and z as fixed, and y as the variable. So we have y plus h and z minus a function at x, y, and z over h. And similarly, taking the partial derivative of f with respect to z gives the limit as h approaches 0, and this time we're fixing x and y, and z is the variable. So we have z plus h minus a function of x, y, and z on h. And similarly, when we evaluate this partial derivative at some point, so we have the coordinates xp, yp, and zp, then we take x, y, and z as the coordinates of that point. So we have yp and zp. And similarly xp, yp, and zp, where we're evaluating the partial derivatives. And the same thing applies to the other partial derivatives. Just like ordinary second order derivatives, there are second order partial derivatives for functions of 2 variables. And these are denoted in a similar way. So we have the second partial derivative of the function with respect to x, and using shorthand notation we can write this as f xx. So first we differentiate f with respect to x and differentiate again. And similarly we have the second partial derivative of f with respect to y. So the shorthand notation is f subscript y. Now we can also have mixed partial derivatives. So we may have the second order partial derivative of f with respect to x and y. So the shorthand notation for this is f yx. So this states that we first differentiate f with respect to y and then differentiate with respect to x. And similarly, we may have the second partial derivative of f with respect to y and x. So in this case, the shorthand notation is fxy. So we first differentiate with respect to x. So we have df dx. And then differentiate this with respect to y. And we can also have higher order partial derivatives. So we may have the third partial derivative of f with respect to x, and again with respect to x and y. So in this case, we differentiate with respect to y first, then with respect to x, and again with respect to x. So this can be written as df dy, which will differentiate with respect to x, and then we differentiate again with respect to x. And now let's look at a simple example where the function of x and y is equal to x e to the y plus x sine y. So the second order partial derivative of f with respect to x is obtained by differentiating f with respect to x and then differentiating the result with respect to x. So df dx is equal to e to the y plus sine y. Noting that we held y constant. And then differentiating with respect to x, we get 0. And similarly, to obtain a second partial derivative with respect to y, which we'll write in shorthand notation, we first differentiate f with respect to y. So we hold x constant and we get e to the y. And here we have x being constant by cosine y. And differentiating again with respect to y, we get x e to the y minus x sine y. And suppose we want the second order partial derivative of f with respect to x and with respect to y. Well, we'll first differentiate with respect to y, which we've done here, and then differentiate the result with respect to x. So we get e to the y plus cosine y. And suppose we want the second partial derivative of f with respect to y and x. Well, in this case, we differentiate f with respect to x first, which we've done here, and then differentiate with respect to y. So that gives e to the y plus cosine y. And we'll see why these are equal in this case when we look at the mixed derivative theorem. Recall when we had a function of one variable, then we found the existence of the derivative with respect to the independent variable x implies continuity, or that the function is continuous. And in contrast, for a function of two variables, both partial derivatives with respect to x and y can be defined at a point in the domain of the function, but the function may not be continuous. So the existence of the partial derivatives alone does not imply continuity. And a good example is the function of two variables being piecewise continuous. So it's 0 when the product of x and y is not equal to 0, and 1 when x multiplied by y is equal to 0. So therefore, this line over here is obtained when x is not 0 and y is 0. So the function evaluates to 1. And for the function where x is fixed at 0 and y is variable, then that also evaluates to 1. So we get two perpendicular lines. Now at the origin, the function evaluates to 1, but the limit of the function as the point with coordinates x, y approaches the point at the origin does not exist. So we can see this by the two-path test. So for example, if we approach the origin along this line, the limit evaluates to 1. And if we approach the origin along this line, then the limit evaluates to 0. So therefore the function is not continuous at the origin. But the partial derivative with respect to x, so we walk along this line over here to the origin, and the slope of this line is 0 all along the line. So the partial derivative with respect to x at the origin is equal to 0. And the partial derivative with respect to y evaluated at the origin, so we're instead walking along this line, is also 0. So both partial derivatives exist, but that did not imply continuity. Now if we take a point along this line through the origin in the neighborhood of the point at the origin, so that's given by this function where x is not equal to 0. So if we take the partial derivative of the function with respect to x, it's constant along this entire line. And taking the partial derivative of f with respect to y, so this time we're walking along the y direction, we see there's a jump discontinuity. And therefore, this partial derivative does not exist. And similarly, taking a point in the neighborhood of the point at the origin, so along the line x equals 0, which is defined by this function, so we're taking the point in the neighborhood of the origin, so where y is not equal to 0, then the partial derivative of the function with respect to x, so we're walking towards this point along the x direction, and we see a jump discontinuity. So this partial derivative does not exist. And if we walk along the y direction, then the partial derivative of the function with respect to y is constant. So as we can see, it's 0. So therefore, taking an open disk that's centered around this point, then for the function to be continuous, the partial derivatives must exist in the neighbourhood of this point. So we come to the conclusion that the partial derivatives must exist and must be continuous throughout the disk centered at the point. So in the neighbourhood of the point where we're checking for continuity. So therefore, if the partial derivatives exist and are continuous, then that implies the function is continuous at this point. And more generally, if both partial derivatives of this function are continuous throughout an open region in the domain of the function, then the function is differentiable at every point in that region. If a function of two variables and its partial derivatives with respect to x and y, and also the mixed derivatives with respect to x and y and x, are all defined in the neighbourhood of a point P, so a small open region surrounding this point. So P has coordinates x and y, so these are defined at P. And if they're also continuous at P, then taking the partial derivative with respect to x first and then y at the point with coordinates xp and yp is the same as taking the partial derivative with respect to y and then x at the same point. So this is called Clairaut's theorem. So this theorem can simplify our calculations considerably. So for example, suppose we have a function equal to e to the x cosine x on x squared plus 2 minus xy squared, and we want to evaluate the second partial derivative of z with respect to x and y. So if you evaluate the partial derivative with respect to y first, so we get minus 2xy, and this complicated term drops out because we're holding x fixed while taking the partial derivative with respect to y. And therefore, if we now differentiate with respect to x, so we first differentiated with respect to y, and now x, so that gives minus 2y. Now in contrast, we could have differentiated with respect to x first, and then y. So if we first take the partial derivative of z with respect to x, then the first term evaluates to a function of x using the quotient rule, and the second term evaluates to minus y squared. So we held y fixed while differentiating with respect to x. And therefore, if we now differentiate with respect to y, this complicated function drops out, and we obtain minus 2y. So both mixed derivatives are equal, but evaluating the first one is a lot simpler. Let's evaluate the following partial derivatives for this function. So using the double angle trig identity, we can write this as 1/2 plus 1/2 by the cosine of 2 multiplied by this expression. So we have 4x plus 6y. And therefore f subscript x is the partial derivative of f with respect to x. So we're holding y constant, and the first term drops out. So we get minus 4 on 2 sine 4x plus 6y. And the partial derivative of f with respect to y is minus 6 on 2 sine 4x plus 6y. And now we find the second partial derivative of the function f with respect to y first, and then with respect to x. That's the same thing as a partial derivative with respect to x of the partial derivative of f with respect to y. So essentially, we're differentiating this partial derivative with respect to x. So that gives minus 12 cosine of 4x plus 6y. And the second partial derivative of f, firstly with respect to x, and then with respect to y, is the partial with respect to y, but the partial derivative of f with respect to x. So this partial derivative was evaluated, and we take the partial with respect to y. So that gives minus 12 by cosine 4x plus 6y. So because the function is continuous, and these partial derivatives are all continuous, then the mixed derivatives are symmetric as expected. Let's evaluate the partial derivative of the function f with respect to y at the point with coordinates 2 and 3 using the definition of the partial derivative. So we take the limit as h approaches 0 of the difference quotient. So first we have the function of x being held constant and y being the variable. So we have 3 plus h and minus a function at x equals 2 and y equals 3 on h. So that gives the limit as h approaches 0, and our function here is 3 plus x multiplied by y minus 2 by x squared multiplied by y. And let's make a bit of room. And then we subtract the function evaluated at 2 and 3. So I have minus 3 minus 2 minus 2 by 3, which is 6, and minus 2 by x squared by y on h. So 3 cancels, and 2 cancels, and 2 by 3 is 6, cancels with this 6, and this far term should be positive because we're subtracting the function, so we have minus minus, and therefore this term cancels with this term, and what we get is the limit as h approaches 0, and we have 2h minus 8h, which is minus 6h on h. So the h's cancel, and the limit evaluates to negative 6. And you can verify this by taking the partial derivative of the function with respect to y. So these two terms drop out, and we get x minus 2x squared. And evaluating this at the point with coordinates 2 and 3. So we get 2 minus 2 by 4, which gives negative 6. Let's evaluate the partial derivative of z with respect to y at the given point. So evaluating the first term, we hold x fixed, so we get 2x squared. And for the second term, we'll use the product rule, as well as the chain rule. So we get 2z by the partial derivative of z with respect to y multiplied by y minus z squared by the derivative of z with respect to y, which is 1, and plus 2x, which is constant, by the partial derivative of z with respect to y, and that's equal to 0. And now we can group the terms. So we have 2x minus 2yz by dz dy, and that's equal to z squared minus 2x squared, and then dividing through by this term, we get 2x minus 2yz in the denominator. And now we can evaluate the partial derivative at the point with coordinates 2, 3 and 1. So z is equal to 1, x is equal to 2, and that's divided by 2 minus 2 by y by z. So 1 minus 8 is negative 7, and 4 minus 6 is negative 2. So we get 7 on 2. Show that the following function of x and t satisfies the wave equation. So in this case, t represents time. And note that c is the wave speed. So differentiating w with respect to time, we get c by cosine x plus c multiplied by t. And differentiating again, we get the second derivative of w with respect to time. So that gives minus c squared by sine x plus ct. And differentiating w with respect to x, we get cosine x plus ct. And differentiating again with respect to x, we get minus sine x plus ct. So on the left hand side, we have this expression, and on the right hand side, we have positive c squared by this expression. So both sides of the equation are equal.